Hey guys, so in this video I'm going to go over the definition of a concave and a convex function and how they kind of relate to each other. So what I'm going to do is get straight into it by writing out the definition of what a concave function is. So this is what the definition is going to look like, and at the moment you guys are not going to know what this means, which is okay, because the whole point of this video and what I'm going to do in this video is break down this definition so that by the end you guys kind of know it inside out. You know exactly what it means, you know every single aspect of it, and how it relates to a concave and convex function. So this right here is the definition. This whole equation, this is going to be the definition of a concave function. And once you guys understand this, the definition of a convex function is going to be the complete opposite, which is that. So once you understand this definition, you can understand both the convex and the concave function fairly straightforward. So what I want you guys to do now is completely forget about the inequality that I just drew on the previous slide. I'm going to now kind of look at it step by step. I'm going to break it down, each aspect of it, and we're going to start from scratch. So the first thing that we're going to need to kind of know is what we mean by a convex set. Now, a convex set and a convex function are two different things. But once you understand what a convex set is, we're going to use that in the definition of a concave and a convex function. And that's how we're going to basically define convex and a concave function. So understanding what a convex set is going to be very important, and it's not too difficult. So we're going to start with some variable lambda that is going to be contained in the set or the interval 0, 1. So lambda is going to be something that can be greater than or equal to 0 and is less than or equal to 1. So at the moment this is just some random variable with not much meaning, and what we're going to do now is define what a convex set is using lambda. So let's just imagine a number line for a moment. That's a terrible line. Let me just make this line a little straighter. So let's just imagine a straight line, a reasonably straight line. That was better. That is, say we have two variables on this line, x, which is, say, 2, and then we have y over here. Let's say y equals 4. And this is just a line of numbers. Let's say 1 is over here, 5 ends over here. This is just a set. What we want to do now is take something called the linear combination of these 2 points, of any 2 points contained in any set here. This is our set, say the number line, this is our entire set. A linear combination of any 2 points within the set, so point y, point x, is going to be the following. So we take lambda, we multiply it by x, and we plus 1 minus lambda and multiply it by y. This is what we mean by the linear combination of any 2 points within a set. So let's say in this case, let's set lambda equal to, say, 0.2. What this is going to mean is that the linear combination of these two things, when we plug in x equals 2, we're going to have 0.2 multiplied by 2 plus 1.8 multiplied by 4. Which means our linear combination with these values of lambda equaling 0.2, y equaling 4, x equaling 2, our linear combination is going to equal, I think, 3.6, which is what happens when you just plug in all these numbers into this right here. So what does that mean? What was the point of that? So what this is doing is, it doesn't matter, we can pick any lambda as long as it's in between, it's contained within this interval here, which is why we kind of laid out this definition to begin with. It's as long as lambda is in between or equal to these two upper and lower bounds, in between 0 and 1, any number that we plug in is going to be somewhere in between these 2 points. So what I'm going to quickly do now is kind of draw this in a different way in a set. So let's say we have, this is our set. Instead of being a number line, it's a circle. And we have 2 points x and y, again picking 2 points in the set. We can pick any lambda, and as long as lambda is any number between 0 and 1, or equal to 1 or equal to 0, a convex set means that we can draw a line between these 2 points. We can draw a straight line between 2 points in a set, x and y. And that's what the linear combination, which once again I'll draw over here, that's what the linear combination is. It's basically just drawing a straight line in between these any 2 points in a set. So an example of a set that is not convex is, say that we had some sort of weird set of numbers that looked kind of like this, if you were to draw them, like a set that looked like this. This is the space. And you had 2 points here, x, and another point here, y. As we can see now, when we have a line connecting these 2 points, that should be straight. When we have a straight line connecting these 2 points, the containing 2 members of the set, it's not contained within the set. This line segment is not contained within the set entirely, which means the set is not convex. So going back to this example, because this set here contains the line segment between 2 of its members, x and y, these 2 members of the set, because it contains its entire line segment, it is convex. Whereas this set is not convex because it doesn't contain the entire line segment. As you can see, it dips out of the set here. Whereas in the number line example, as you can see, this entire set here, 1 to 5, is the entire set. We can pick any linear combination and it'll all be contained within the set 1 to 5 still. So that is a convex set. So now, knowing what we know about a convex set and linear combination of 2 points within a set, let's use that knowledge that we've just learned and now just look at a simple function that we're going to draw on a simple 2-dimensional graph with our x-axis here and our y-axis here. So let's say on the x-axis, let's pick 2 points here, point x and point y. So these again are 2 points contained within our set, with the set being the x-axis. Now let's say our y-axis is some sort of function that maps these points here into the y-axis. And let's say the function looks something like this kind of curved shape. Let's map our points on the x-axis to the y-axis based on the shape of this function. So this is what the f of x is going to be. Let's say we have y over here. Let's make this as straight as we can. This is where f of y is going to end up. So we have 2 points on the x-axis and we have a function which is going to kind of dictate where these 2 points on the x-axis get mapped to on the y-axis. So there's our function of y, which is where y meets the function, our function of x here, which is where x meets the function. So now let's start by taking the linear combination between x and y, which as we know is going to be this. Let's write it out once more. And let's just call this now L, just so we don't have to write this out every time. Let's call this L. So let's put L, let's pick any lambda. Remember now at lambda, I'm running out. So that's lambda, which is just, again, I've written this about 3 times, is just going to be contained within the interval 0, 1. Let's take a linear combination between x and y, which, as we know, is going to end up between the 2 points. So let's say right here, smack bang in the middle. We take our linear combination. Let's now map our linear combination to the function that we've just drawn. Now this over here is going to be f for L, so the function of the linear combination. So I'll just write this out I'll elaborate on that. So that's what this is here. We've taken a linear combination of 2 points on the x-axis and we've mapped them in the function. So this is what this is here. These two things are identical. So now what we're going to do is again take the linear combination of 2 points on this graph, but this time we're not going to take the linear combination of x and y on our x-axis because we've already got that here, which we've just called L, and we've got the function of that over here, which we've just called f of L. Now we're going to take the linear combination of these 2 points, the function of x and the function of y. If we take the linear combination of these 2 points, we're going to get some point again that's going to be contained within the 2. So let's again take some lambda that means that we end up nicely in the middle between the 2 points. And this is going to be, I have to write this a little smaller, sorry if it's hard to see. This is going to be the linear combination of the functions. I'll write this out here. So this, right out here so it's a bit clearer. This is going to be the linear combination of f of x and f of y, which is going to end up in between the 2 points. So now we have 2 key things that we're going to you guys are going to need to understand in order to know what we mean by, say, a concave function, which would then lead us to a convex function, is we've got the function of the linear combinations, f of L, which is this here, and we've got the linear combination of the functions, which is going to be in between the 2 functions. And again, the first one was in between the 2 points, and now the second one's in between the 2 functions, because remember now when we take a linear combination with lambda e being contained within 0 or 1, it always ends up between our 2 points that we're looking at. So the linear combination, what we're going to do is we're going to draw just another line. I'm not going to draw any more lines after this before it gets a bit too confusing, but I'm just going to draw another line here. It's going to be a nice straight line from point x to point y. This is our line that is going to be the linear combinations of the functions. So let's say this one ends up right here. If we picked another linear combination, let's say here, it would be to there, etc. That's what this dotted line across here represents. Is when we take the linear combination of these 2 functions, it's going to be along somewhere on this line. As we change lambda, we're going to move up or down this line. So I've just drawn this graph again, hopefully a little bit clearer, because I realized that was probably quite a lot to take in. So I'm just going to go over it one more time now. So here is our linear combination of the 2 points, and here is our linear combination of the 2 functions. And here is a line that is going to tell us, this is kind of the line of the linear combination of the functions. So as I just said, as we change lambda, we'll move up or down this line, and this line always has to be in between our 2 points, because this is what we're taking the linear combination of the 2 points, f of y, f of x. As we can see, it's a straight line, hence why it's called a linear combination in the first place, because it's linear. So this particular function, if you haven't realized by now, just by the shape of it, this is a concave function. It's all good and well knowing that just by looking at it, it's concave because it's got that kind of curved shape, it's got that cave-like shape. But we're not interested in just looking at it and being like, yeah, it's concave. We want to actually formally, mathematically, prove it with the formal definition. Because once we can actually prove that a function is concave using this kind of pretty robust definition, we can be a lot more confident that the function is actually concave instead of just looking at it and being like, yeah, concave. So as we can see here, the linear combination, the function of the linear combination is greater. This point here is greater than this point here. So in our definition of a concave function, this is what we have. So in order to understand this a little bit better, we can kind of test this. We can, put this definition through some tests to see if it holds up. So let's kind of put this definition that we went through over at the beginning that I said was the definition of a concave function. Let's put it through some tests using our example that I've drawn below. So let's kind of test this out by picking different types of lambda. So let's look at the very extreme end, for example, where lambda is equal to 1 or 0. If lambda is equal to 0, looking at our linear combination here, we'd have the x cancel out, and we would have just 1 multiplied by y. So if lambda was equal to 0, our linear combination would just be here, wouldn't it? It'd be equal to where y is right now. Likewise, if lambda was equal to 1, our linear combination would be here. So in this case, the key point to remember is, now bringing back our definition of a concave function, is that it's greater than or equal to the linear combination of the function. That's the key point. It's greater than or equal to, because in this case, back again to if lambda was equal to 0, we would find a linear combination that would be equal to the linear combination of the functions, because we'd be right at the top here in red, and we'd be again here with this. So these two would be equal to each other if lambda was equal to 0. Likewise, if lambda was equal to 1. So because they can be greater than or equal to each other, we can find any possible lambda in this example below. We can find any possible lambda, and this inequality will still hold. You can try it yourself. You can try every different type of lambda, combination of lambda. This inequality will still hold, regardless of if lambda is even on the very extreme ends of being equal to 0 or 1, it will still hold. So we know that this is a concave function. Most of you would have already known that just by looking at the shape of it, but now with this definition applied to it, we have proven that this is absolutely a concave function. Because obviously in reality, in real life, most functions aren't going to perfectly look nice shaped like this, so we need more of a kind of robust definition to tell us whether a function is concave or not. So rather logically, now that we've got this definition of a concave function that I mentioned at the very beginning, and now I've brought it back and I've applied it to this example that we've looked at, when you look at a convex function, it is the opposite of this. So it would be the exact same, every element here would be identical, except the inequality would be the other way. So it would be less than or equal to the linear combination of the functions. Because in a convex function, as most of you know, rather than having this kind of cave-like shape, where it's kind of a curve, it's got the opposite, where it kind of has a U shape. It goes up. if we were to kind of draw it on a little mini graph over here, a convex function would look something kind of like this. It would be the opposite shape to this cave-like shape. And so all we have to do is just swap the inequalities around because we're looking at the opposite case. And so, you know, visually, we know they're opposite. One's got this U shape, one's got this cave-like shape, and that kind of transfers over into this definition too, where it's just the opposite case, where we just flip the inequality around. So once you understand the concave function definition that I've kind of gone through, the convex function definition is pretty easy to understand because it's just the opposite case, and that should be quite intuitive for you guys. Another little side note, here, because we've got greater than or equal to, or less than or equal to, when if we were to look at the case of a strictly concave function, basically, you know, it's in what it means is in the definition. A strictly concave function or a strictly convex function, which is what we didn't look at in this case, but they're just kind of small extensions of this definition. All we'd have to do is remove this equal to. So rather than being greater than or equal to, it would just be greater than, which basically, you know, we're just being more strict with the definition. We're not having any leeway. So if we were to pick a lambda equal to 0, we'd find that this is not strictly concave, because in that case we'd have these two things equal to each other, which in a strictly concave case cannot occur. So yeah, that's what a concave and a convex function are. I hope you guys enjoyed that and that you understood it for the most part. If I was unclear on anything or anyone had any questions about this, just put them in the comment section and I'll try my best to answer them. But yeah, hope you guys enjoyed and hopefully that helped.